Can you hear me already or not? I'm online?
Yep.
Okay. Hey, good morning, guys. Alex Rosenbaum from Mellanox. Some of the topics I'll touch are also related. I mean, the topic I'm going to talk about is multi-process sharing of RDMA resources. So I'll dive in. So do we really need multi-process RDMA sharing of resources? Today, we're working hard to make everything very well isolated between processes, trying even to get to single-threaded processes to work very efficiently. So why do we really need suddenly multi-process to access our QPs, CQs, and other RDMA resources? So I'll discuss a little bit about the motivation, different solutions, some examples, and some of the problems we see at this stage with going in this path. So there's no one clear solution that I want to present. There are actually three of them at least now. So where is this needed? So first of all, we just discussed big data, Hadoop, and these frameworks. A lot of these frameworks are traditionally over a network, and they're built with forking and multi-processes. And if we want to replace this and do RDMA instead of TCP/IP for all the shuffle of big data and stuff like that, the frameworks themselves are built on forking processes. So we need some way of supporting forks, of having a web server accept the connection, create the resources, and passing the handling of the data to a worker thread or a worker process in this case. So it depends on the use case. If we're coming into a ready-made framework, telco grade, a lot of more and more telco grades are also going into the cloud, private clouds, and for them, multi-process is essential. Maybe they're correct, maybe they're wrong. It's a different argument, but they require multi-process, and we want to be able to provide them with capabilities to use RDMA in this multi-process environment. Applications want to get updated without breaking connections. Bringing up a new RDMA connection, if we're talking about a big cluster, getting all-to-all connection is a very long consuming process. And if we have these connections up and running, we might want to be able to replace the binary of the process to do more advanced logics, application logic. And we want to be able to do this without breaking the connection. So we want to bring up a new process, try and move the QP, connected QP, to the secondary process, and then we can kill the old process down. So there are use cases for upgrading. And then why just not treat the multi-process as multi-thread? I mean, we want to sync threads, so we can sync processes. There's no reason why not to. I put this at the end, some other use cases are debuggability. If I have a running process and it has all the IB resources isolated, I don't have a really good way of attaching in and seeing what's happening. If I can share these resources between different processes, so basically I can attach a debug process in parallel, pick out data that I want out of this working application, and then when I'm done debugging, just kill the secondary process. And I haven't touched the original process. I haven't killed it. I didn't have to drop it or renew it. So it's another way of adding debuggability without touching the working process. So three models that I want to share. Basically, all three models we see with customers we're dealing with that want one or the other, and they're a little bit different in what they provide and how to implement them. I don't have one solution which fits all today. So I think part of what I'll be interested to hear maybe at the end is if anyone has similar use cases and thinks one is better than the other, or different ones that we didn't do. So the first one I want to discuss is shared IB objects. So in this model, we have one process creating different IB objects, and the primary or the process creating the objects will want to expose some, let's say, a PD or an MR to a secondary process or to 1,000 secondary processes. So it will have to take the PD in user space and associate it in a shared object or open it to be shared, and then pass this information to a secondary process in a secure way, maybe with a secured FD or the FD of the context. And then the secondary process can open the same PD in order to use MRs on the same memory region. So essentially in the kernel, we'll want to have a single hardware object which is exposed from different processes where the process was able to transfer the object value or the object handle to the kernel from one to another and allow a secondary process to access this. So basically, this can work by the primary process, again, opening the RDMA resource, creating a shared file descriptor, and associating it with a IBV context, associate the object it wants to share with the FD, pass the FD to some other process, and the secondary process will open this and get the kernel to expose the same value of the object it's willing to share. So an example which I'm sort of referring to is if I have a very large chunk of memory and I want multiple processes to be able to do different access on this memory. Maybe the memory is segmented and the application logic knows which secondary process will access which part of the memory in order to prevent overruns and locking. So a primary a process will allocate the PD and register the MR, and then for every worker, I will create a secondary process, just hand over the PD and the MR, and that secondary process can actually do RDMA operations on the original MR. If something happens to this secondary process, the connection dies, the process dies, or something happens, I don't have to re-register the entire memory. The memory is not hurt. Basically, I created a single MR, so I have very efficient caching in the hardware. Even if it's 1,000 processes, I had a single PD and MR entry, so the QPs can be created on the PD, the secondary QPs, and the MR is a single one, so I have very good access to the cache. So this is one model where I shared the PD and the MR to multiple other processes. At least at this point, it's very well understood for objects which are stateless, because I just gave the handle, the kernel handle, to another process. But what happens if it's a stateful object? What happens if I want to re-register the MR and modify the capabilities? How do I update the secondary process that this changed? What do I do with a QP, CQ, and other objects which have a real state? How do I sync the states between processes? So this has advantages for some objects, and very simple. I can run different kind of processes. They don't have to know each other or be the same kind of binary. So shared object is the first example. Second is fork solution. Today, in RDMA core, the main thing we have is the application can declare it's not doing fork, and we can prevent or limit fork from touching the memory or the hardware resources, so we don't get hurt. But in this case, I'm talking about real fork. If you had a TCP socket and the application fork, both parent and child can send or receive on that TCP connection. So that's what we want to try and achieve by doing real fork. Basically, parent process creates the IB or the RDMA resources, and when the parent forks, the child, if these resources were created on a shared memory managed by the RDMA core library, so all the verbs object, RDMA CM objects, the underlying vendor objects or provider objects, all are created on shared memory. The moment fork happens, both child and parent have access to the same objects which are managed in sync on the shared memory. So all the states are synchronized. Obviously, I have to have the FD, which is mapped, the memory, which I said will be allocated on shared. Locks have to be not just thread locks, they have to be inter-process locks. And then different threads on the child process and a parent process can sync between them when accessing. I would say that similar to a single process where we have multiple threads, for performance, we don't really want multiple threads accessing the same QP-CQ because we're going to have contention there. Probably in this case as well, we'll not want to have multiple processes accessing the same CQ-QP. We can protect it, but it doesn't make sense just as we want a single process to have less contention. But if the parent created a connected QP and passed it on to a worker child can use it, and when it's done, just exit, and the QP-CQ are still at the parent's holding. The parent can create a new fork and give it to a different child to do some other work now if new request came in. So basically in this case, we have a single instance of the user space objects managed directly with a single kernel object. Obviously, if the child would do a destroy QP, the parent QP will also be destroyed, but that's true also for multiple threads in a single process. If one thread destroys a resource and doesn't sync with the other thread, it's going to be a similar problem. User has to deal with inter-process syncing, update the child process, parent process, who's doing what, just as it would do with threads. With threads, it's a little bit simpler because they can share the memory. Here, they have to develop inter-process communication, which is a little bit more complicated, but not much. In a very high-level potential API for this would be that instead of just open device with the flag which says, I want this context to be shared. And from this instance, this IBV context will allocate all the resources it's managing and the provider underneath it accessing that device on a shared memory allocated block of memory. All the locks have to be created as inter-process locks and not just regular semaphores or mutexes, spin locks. And once this is done, basically fork is supported. I mean, that's all we have to do, create QP, and anything in the following the create QP, CQ, PDMR will just go to the child process as it would. So it's a very rough drawing of two applications accessing the same post send. If there's a lock there, it's protected. And they can both send and then pull CQ or whatever they want to do. This is like a very pseudocode example of what's happening. The main server thread will create the resources as a shared context. We'll open a listen, RDMA listen ID, wait for a new request. When a new request happens, it will create the QP-CQ, accept the connection, and fork and let the child manage this QP-CQ. And when the child is complete, the child can kill the resources and leave and exit the process. So this is a classic web server handling of TCP connections. We can do this also with RDMA connections. Some limitations. Obviously, there's no perfect solution. There's always cavities. So main cavities, if we're forking, we have a single binary instance of the application which manages parent and all the child's code. We cannot have a different one to run the child process. It's always a single process. If we want to upgrade, for instance, in the first solution where a secondary process can have access or share objects, we can have totally different binaries. They just have to sync between who's opening the object to be shared and who's receiving the object that is shared. In this case, it's a single binary. There's no upgrade process. We have to kill from the parent, and all the resources are gone before we initiate a new process. We cannot add new resources to an already created child. So if we have a child and it's using something and it wants more resources, the parent cannot provide it because the memory is already forked. We cannot resync them later on. We can kill that child and create a new child. That's always a possibility, but we cannot add more resources to the secondary process. Again, with a shared object, at any point in time, we can add or take more resources out of the shared resource pool. There is a question, I mean, when you work with multiple threads and there's a bug, I mean, all this is also, when I say telco grade, if one process dies, we want to be able to keep the object. So if we were doing multi-thread, one thread has a bug or something wrong and it dies, the whole process terminates. So we don't really maintain state in the hardware, driver, or the application. Everything is released. When you have multiple processes and somebody just did poll CQ and crashed, so how do you maintain hardware state? How do you maintain driver state? Did I poll the CQ? Did I poll the completion or not? And if already driver and provider and hardware are synced, the application just got a completion and it died. It doesn't know, the parent won't know what's the state of the QP-CQ to have another process continue that. What's nice about this solution is the API is simple. It's one flag and everything is shared. Any new object we create in the future falls under this category of sharing. You don't have to make dedicated APIs for sharing MRPDs, maybe different APIs for sharing QP-CQs. So this is a very simple API for sharing everything. It fits a fork model. It doesn't fit other models. A third solution, which is close to the fork model, some more complications and some relaxation of things, is just having shared memory on the application level. So MPI has a lot of shared memory infrastructure. DPDK provides shared memory infrastructure as well. Instead of having the libverbs RDMA core manage the shared memory up until fork, the application can manage the shared memory. Once the application does that, it knows how to sync different processes into the shared memory area. This means that application will provide memory for the RDMA core library. Objects similar to what I presented in fork, the application, the library, once creating a resource, the library will request memory on the shared slab from the application. Any secondary process can join. So now it doesn't have to be a single binary. I mean, with fork, it's a single binary that forks. Now the application manages the shared memory. So a secondary process with a different binary that has the same shared memory logic and the same RDMA core library can join into an already given shared memory and access things. So, so the sharing of resources on shared memory is still there, but we're opening it up to different kind of applications to share it. We're not limiting the solution to fork solution only. Applications can get updated. The secondary process can go up, take control of all the shared memory, and the old process can die, can exit. And we upgraded the application logic in this way without terminating any connection, without hurting the RDMA service. We still have to keep the RDMA core in the same version. If we change this and something change in the data structure, obviously this will break. So a very example similar to the fork, on every new a connection coming in from the RDMA CM, we create more resources, QP-CQs, we accept the connection, we launch or upgrade processes which will attach to the shared memory, and again, inter-process communication have to tell the secondary process, please use these resources that I created on the shared memory area, and that's what you're supposed to do, don't touch this. So API is very simple again. We have to create allocation and free macros or APIs to replace the in-library allocations, and application just places all resources on some shared memory. This is more complicated for a simple application because suddenly it has to manage shared memory. And there are complexities in managing shared memory solutions. Limitations. With fork, the virtual address space just replicates, and it's same pointers. We don't have to deal with offsets. Objects sit in the same virtual address. They point to other objects which have the same virtual address. Everything is the same. Nothing changes between the processes. When we're dealing with shared memory, by default, Linux will try and map the shared memory in different offsets. So we have to disable this, alternatively change all the objects to use offsets, which is very complicated. We have to guarantee a RDMA core binary compatibility, so nothing must change. Any type of structure that changed will break how the shared memory is being read and processed, and this will break the solution. Again, we have the same atomicity problem. If one process accessed a completion queue, a QP, and did something bad and died, who maintains the state of the hardware, driver, application logic? Who knows where things are? It's a little bit different when you deal with TCP, which is fully managed in the kernel and keeps the state of the TCP connection. Okay, so I discussed these during the fork and so on. Okay, so that's basically it, the three ideas for fork. Again, with big data, we see fork usage, and we want to be able to add RDMA in a simpler way to be able to handle this. We see telco customers that would like to use RDMA capabilities, and again, also go to the cloud in some cases, probably private clouds to start until security advances. But they will also want to have some sort of fork or multi-process capability. We see customers that want to be able to maintain the connection. If they have a large all-to-all network, they don't want all the RCQPs to fall if one process dies. They would like to split the service into 10 processes, and if one dies, so 10% of the service died, but it's easy to reactivate it. They don't have to kill everything for that. So we see different kinds of requests out there for multi-process. I don't know if we have to do all of them or some of them, or start with some and overcome the issues as we move forward with them. Okay, questions?
There's a mic in the middle. If people have questions, can you please walk up to the mic in the center? Thank you.
Have you ever any thought of multiple shared memory zones so that you could fork and have a shared pair with the child, and then fork separately on a different shared memory zone and have isolated children pairs?
We didn't go that far because I would think if you look at a regular TCP connection-based fork solution, so it's a similar problem. If the parent would close some of the resources, the second child won't have it. So if you create a so it's a different sort of problem. Yeah, so that's something that needs to be maybe added as well with a fork solution. So you can have different children do different things without hurting one another.
Right. I think if you can solve that, you actually get the solve server worked out.
Mm-hmm. Yeah. Okay.
So my question is related to trade-off between scalability and performance. With the current model, it looks like the resources are shared, right? And there are a set number of dedicated resources available too. So how do you do a trade-off between when to switch from dedicated resources to shared resources to avoid locks and other limited resources, right? So do you have any kind of automated transition between dedicated to shared resources, or is it all up to the applications to handle?
So basically, it's up to the application to decide. I'm not sure I fully understood the question, but basically, each of these frameworks allows just gives the capability for the application to share the resource between processes. I mean, if you have a QP and you have 1,000 processes trying to post receive, post send, there's going to be contention there. So obviously the application has to be built just as it would be designed with multiple threads. How many threads do you want to do send, receive, process completions, and so forth? You would have to design for same performance considerations with multi-processes.
Follow-up question. What about security? Because when you are forking and trying to access, it might work because it's the same user. But what about if it is different users?
So it depends on the solution. Basically, you provide, all these solutions have to provide the access to the admin or to the creator of the resource. So if I'm the parent process and I created a context with the shared and I forked, so I knowingly allowed the child access. Don just suggested maybe have multiple subregions, so I can fork one child with certain resources and a different child with other resources. So that's something we have to design into the solution so we can segregate the different children apart. With the first model where you share object, the creator of the resource has to provide the secondary process these handles in order to open the shared resources. So it's up to the application to decide who's attaching and who wants to do this. So basically the application logic will have to decide, the one creating the resource will have to decide who is it allowing to access these resources which it's giving out. We still have the isolation per process, it's just now that we're allowing the resources to scale up to multiple permitted or trusted processes.
Thank you.
Okay, thank you.